Hello, this is problem set number 3, problem 7. The figure shows a PV diagram of 0.004 moles of ideal hydrogen gas. The temperature of the gas does not change during segment B, C. Or in other words, the temperature of the gas does not change from state B to state C. Right, so it's an isothermal process from state B to state C, which is this path right here between states. Okay. Part A, what volume does this gas occupy at point C? So for part A, we're looking at the volume at state C. Okay, let's write down our givens. We know that the number of moles is equal to 0.004 moles. We know that we're dealing with an ideal hydrogen gas, right? So that means it's diatomic because of this subscript 2 right here. Okay. And we know that from state B to state C, the temperature doesn't change. So it's isothermal. So TB is equal to TC. Okay. All right, so for part A, to find the volume at state C, I'm going to use the ideal gas law. Okay, that's PV equals nRT, right? And if we go from state B to state C, we will find that PB and VB is equal to nRTB, right? And PC, VC is equal to nRTC. However, again, we're dealing with an isothermal process from state B to state C. So that means constant temperature, so temperature doesn't change. So for that reason, I'm going to just say that these, the right side of the equation here, are constant. They'd never change. So because they don't change, at least from state B to state C, we can conclude that PB, the pressure at B, times the volume at B is equal to the pressure at state C times the volume at state C. Right? So I can just plug in. Do I know any values? I'm looking for the volume at C. Pressure at C, that's given in the PV diagram. Volume at B, also given in the PV diagram. And same with the pressure at state B. Okay? So let's plug those values in. Okay? So PB is equal to, actually VC would be equal to pressure at B times volume at B divided by pressure at C, right? And that's equal to 2.0 ATM times 0.2 liters divided by, what's the pressure at C? 0.5 ATM. Okay, and I got all these values, PB, VB, and PC, using this PV diagram, right? Because the PV diagram provides the pressure and volume, right? So just read the diagram and you can get those values. And if you plug that in the calculator, you will find that the volume at C is equal to 0.8 liters, right? Because my units cancel out, ATM and ATM. Okay, so that's part A. Problem 7 is an extremely long problem, but it's not very complicated. It's kind of simple, right? It's just very tedious and long. Okay, so for part B, find the temperature of the gas at point A, point B, and point C. So what is the temperature at state A, temperature at state B, and the temperature at state C. Okay? I'll start looking for the temperature at state A, again using the ideal gas law. So pressure at A times volume at A is equal to the number of moles, which is constant, R, which is constant, and the temperature at A. Okay? Let's see what we have from the PV diagram. Do we have the pressure at A? Yes, we do, 0.5 atm. Do we have the volume at A? Yes, 0.2 liters. N, that was given to us right here. And R, we should know that if we don't, right? So really, we have everything but TA, so we can solve for TA. By the way, I'll write this down, and this is just something we should always know. R is equal to 8.31 joules per mole times Kelvin, which is also equal to 0.08206 liters times atm over mole time Kelvin, right? And these are both equal values. You can make your choice on which one you want to use for R, depending on what units you're trying to cancel out. All right, so what is PA? PA is 0.5 atm, VA is 0.2 liters, N was given to us as 0.004 moles, and looking at my units, I have atm, I have liters and moles, so I'm going to choose this version of R because I have liters and atm in the numerator, so I could cancel those out, right? All right, so R is 0.08206 liters times atm over mole times Kelvin. And I'm looking for my temperature at state A, right? So I can use algebra and move these two guys, divide both sides of the equation by these two values, right? And I would get TA. So TA is going to be equal to 304.66 Kelvin. Okay? And that's because I divide the left side of the equation by 0.004 moles and also 0.08206 liters times atm over mole Kelvin. Then I'd just be left with TA, right? So then I can find my TA. All right. Now to find temperature at B. And remember, guys, once I know my temperature at B, I also know my temperature at C because the states B and state C, that path is an isothermal process, so they have the same temperature, right? TB is equal to TC. So let's look for temperature at B. Again, using the same ideal gas laws formula. So pressure at B times volume at B is equal to N, which is constant, R, which is constant, and temperature at B, which is what I'm looking for. So looking at the PV diagram, what is the pressure at B? Pressure at B is 2.0 atm, right? And volume is 0.2 liters, is equal to N, which is 0.004 moles, equal times R, right, which is 0.08206 liters times atm over mole Kelvin, times TB, the temperature at B. So again, I divide both sides of the equation by N and R, or 0.004 moles and 0.08206 liters times atm over mole Kelvin. And I would find my temperature at B, which is actually also my temperature at C because they're isothermal, right? Temperature is constant from B to C. And that would equal to 1218.62 Kelvin, right? remember it's isothermal process from state B to state C, constant temperature. Okay. All right, so I think that is all for part B. Let's move on to part C. And the problem is asking how much heat went into or out of the gas during segments AB, CA, and BC. Indicate whether the heat went into or out of the gas. What does that mean when something goes into or out of the gas, right? So remember that, what was that? Part C is heat. So heat transfer is Q, right? That's a symbol for heat transfer. And Q is positive when heat goes into the system, which in this case is the gas. And it's negative when heat leaves the system or the gas, right? Okay, so that's how we can indicate whether the heat went into or out of the gas. Is it depends on the sign of our Q, our heat transfer, right? If it's positive or negative. Okay, so let's look at, we have to find the heat transfer from A to B, the heat transfer from C to A, and the heat transfer from B to C. Okay, that's what the question's asking. So I'm going to start with state A to state B, okay? So we know that from state A to state B, right here, that's an isochoric process, right? Or constant volume. And we know that because it's a straight vertical line. That means the volume was constant from state A to state B. What else does that tell us? That tells us that work of the system is zero because the work is the area under this curve, right? And there's no area under the line from A to B because it's vertical. So I can say that A to B is an isochoric process, or constant volume, right, from VA is equal to VB. So what do we know about how can we find Q, or heat transfer? We can use the first law, right? So the first law is the change in thermal energy is equal to heat transfer minus the work by the system. Okay? And if you guys didn't know this formula right here, first of all, I hope you guys do know this formula, but if you don't, try to watch the chapter 19 summary that I posted, that it'll talk about all these formulas that I think you need to know, or helpful information. All right, so we just said for an isochoric process, work is zero, right? Because there's no area under this vertical curve right here. Volume is constant. So in this case, this is zero. So if we find the change in thermal energy, we would also find our Q because they're equal to each other, right? And what do we know about Q? What do we know about the change in thermal energy? So change in thermal energy is equal to the number of moles times the molar heat capacity for constant volume times change in temperature, right? Another way we could write that, so if we find this, then we would also find the Q that we need from A to B, right? However, the molar heat capacity for constant volume was not given in this problem, so I need to find a way to find that, okay? And if you look at chapter 18.4, heat capacities, we talked about the different values for molar heat capacity for a monatomic gas, diatomic gas, or polyatomic gas. And in this problem, we deal with a diatomic gas, right? H2. That's diatomic because of the subscript 2. So the value for molar heat capacity for diatomic gas is actually CV is equal to 5 over 2R, okay? And that's just something we should know or have in your cheat sheet. Again, see the chapter 19 summary video if you guys need more help with that. Okay, so we can actually plug in this value for CV right here. Okay, and then we would get the change in thermal energy is equal to N times 5 over 2R times the change in temperature. Okay. We know the value for N, we know the value for R, and we know the value for the change in temperature, right? So actually we could find our Q from there. So that is equal to N, or 0.004 moles, times 5 over 2. And I will use the value for R as times 8.31 joules over mole times Kelvin, okay? Because I want to end up with joules for this problem. And then the change in temperature, I'm going from A to B. So the temperature at B is equal to 1218.62 Kelvin minus the temperature at A, which is minus 304.66 Kelvin, okay? Again, this is the temperature at B, and this is the temperature at A. Okay? And if I plug that in my calculator, I would get times 8.31. I would get that my change in thermal energy, which is also the value for my heat transfer, is equal to 75.95 joules, okay? And that's positive. Whoa. That's positive, okay? So that is my heat transfer from A to B, okay? Was that all the question was asking for? Indicate whether the heat goes into or out of the gas. Again, the sign for the heat transfer is positive. Therefore, heat went into the system, into the gas. The gas is our system, right, in this case. Okay, awesome. So now let's look for the heat transfer from state C to state A. Okay? One sec. Okay, so state C to state A. What can we see from state C to A? Looks like our pressure is constant, right? It's an isobaric process because it's a straight horizontal line. So state C to state A is isobaric, which means PC is equal to PA. The pressure doesn't change, it's constant. And remember, in, I think it's chapter 19.4, that is internal energy and first law of thermo. It said that for an isobaric process, okay, but I'll use blue. Okay, so for an isobaric process, meaning constant pressure, Q is equal to, this is only for isobaric, Q is equal to N Cp delta T, okay? So that's the number of moles, molar heat capacity at constant pressure times the change in temperature, okay? Again, it wasn't explicitly given that the value for Cp right here, right? So we can use what we know, right? And we know that Cp, or rather we know that Cv, the molar heat capacity for constant volume, is equal to Cp, which is the molar heat capacity for constant pressure minus the constant R, right? So we could add R to both sides and we would get the value for Cp, right? So in this case, we get Q is equal to N, and the value for Cp would be multiplied by Cv plus R, okay? Cv plus R, and multiplied by the change in temperature. Okay. Again, we don't know the value for Cv, but remember this fact from chapter 18, section 4. Cv is equal to 5 over 2R. So let's substitute that in. So N is equal to C, rather than Cv, we'll write 5 over 2R plus R, and we'll call that 2 over 2R, right? Because 2 over 2 is just 1, times change in temperature, delta T. So then we get N times Cp is equal to Cp equal to Cv plus R, right? Okay. So it's equal to 7 over 2R times delta T, right? So then we'd get that is equal to 7 over 2 N R delta T. Okay. And on a side note, we can see that if we look at the change of the ideal gas law, PV equals nRT, right? And again, this works like a derivative. We can bring out the constants. Okay, so this becomes, for an isobaric, pressure is constant, so P delta V is equal to N and R are constant, delta T, okay? So that's what happens there. And if you see here, NR delta T and R delta T, right? So we will substitute in, we will substitute in this and this with PV delta V. So that is equal to 7 over 2 pressure times delta V, okay? And that is equal to 7 over 2, and the pressure at C and A is equal, constant, at 0.5 ATM, okay? At 0.5 ATM times change in volume, and that is, what is a change in volume from A to C? Did we solve for volume? Yes, we did solve for volume right here. So in part A, we solved that volume at C is 0.8 liters. So we'll have, since we go from state C to state A, we go state A's volume is 0.2 liters minus state C's volume, which we solved for in part A, which is 0.8 liters, okay? And if you plug that in the calculator, you would get 7 divided by 2 times 0.5 times negative 0.6, negative 1.05 ATM times L, right? And if I want to cancel out my units, so 1 liter is equal to 0.001 cubic meter. And you could just find that on Google and write it on your cheat sheet, meaning this conversion factor. And also this conversion factor, which is 1 ATM is equal to 1.01 times 10 to the 5th pascals. Okay? So 0.001 times 1.01 times 10 to the 5th. So we would get minus 106.05. We'd end up with meters cubed times Pascal, which is a joule. Okay. So from the heat transfer from C to A is equal to minus 106.05 joules. And because the sign is negative, that means the heat transfer goes out. Therefore, heat transfer leaves the system or the gas. Okay. Give me 1 sec, guys. I just want to confirm that that is correct. So QCA, yes. Okay, awesome. All right, and for QBC, or the heat transfer from B to C, that's what we'll solve for now. B to C. what do we know about that? B to C is, again, isothermal right here. Temperature stays constant, right? So this is isothermal now. And what do we know about isothermal? When temperature is constant, the change in internal energy, or the change in thermal energy, is 0 for any isothermal process, okay? Therefore, if you have the ideal gas law, or sorry, the first law of thermodynamics, which is change in thermal energy is equal to heat transfer minus the work done by the system. Well, because this is 0, right? Then we just get that the heat transfer is just equal to, or sorry, not minus, but is just equal to the work done by the system, okay? And for an isothermal process, okay, so this only works if your temperature is constant between states. Work done by the system is equal to N, R, the constant N, the moles, the number of moles, the constant R, and temperature times the natural log of your final volume over your initial volume, which in this case, final volume is the volume at C, since we go from state B to state C, right? Okay. That's in chapter 19.4. You will find this equation, or it lets you know that for an isothermal process, that's how you find the work of the system. Again, that's in the summary for chapter 19 video I posted, so you could see chapter 19 section 4 if you need a refresher on that. So let's just plug in our values. We know that N is equal to 0.004 moles. R in this case, I will use 8.31 joules per mole times Kelvin, because I want my answer to, I want joules basically, so I chose the one with the numerator of joules. Temperature from C is 100 temperature at C is, let's see, 1218.62 Kelvin, and multiplied by the natural log of the volume at C, that's 0.8 liters, and the volume at B, that's 0.2 liters, right? This one, volume at C, we solve for part A, and volume of B is given in the problem, or in the PV diagram. Okay, so if I plug all that in my calculator, the work done by the system is equal to 56.15 joules. And again, the work done by the system is equal to heat transfer, right? So for my heat transfer from B to C, that is 56.15 joules, and positive, therefore heat goes into the system, or into the gas, because the system in this case is the gas. I just want to make sure from the solutions that that's right. BC, yeah, that's right. Okay, cool. Q at BC, right? Yes, 56 joules. Awesome. Okay, now let's find the what else do we need? BCCA. Oh no, we've got everything. Yeah, we've got the heat transfer from AB right here. We've got the heat transfer from C to A right here, and the heat transfer from B to C right here. Okay. Again, guys, I told you problem 7 is so long, unnecessarily long, but it's not that difficult, actually. It's just annoyingly long. So we can move on from part C to part D. Okay, let's see. So part D, find the change in the internal energy of this hydrogen during segments AB, BC, and CA. Indicate whether the internal energy increased or decreased during each segment. Okay. So we're looking for the internal energy, right? Which is another way of saying thermal energy, right? For AB, BC, and CA. All right. I'll start off with the change in thermal energy or change in internal energy from AB, for segment AB. Okay. So from segment AB. Okay. That's what I'll try to find right now. All right. What do I know about segment AB? So the path between states A and B is a constant volume. It's a vertical line, straight vertical line. So it is isochoric, right? Isochoric from A to B. All right. I will use the formula for change in thermal energy or change in internal energy, right? And this you can use for all states. If you have a isothermal process, a constant temperature, right? Or an isobaric process, constant pressure, or an isochoric process, which is constant volume like we have here. You can always use this formula for all processes, okay? That's always true. So you should have that in your cheat sheet. All right, so what is N? N is equal to, well, first, what is CV? Did we ever solve for CV? No, CV wasn't given to us, right? But we can say right here, we know that CV is equal to 5 over 2 times the constant R for a diatomic gas, okay? Which is what we have here. We have hydrogen, we have H2 gas. So diatomic, right? Okay, so N times, for CV, I'm going to use 5 over 2R, okay, times delta T, which is, delta T, and that is equal to temperature at B minus temperature at A, right? Okay, so moles, or I'll bring out my constant first, 5 over 2 times moles, that is 0.004 moles, times R, which in this case I'll use 8.31 joules over mole times Kelvin, and TB is equal to 1218.62 Kelvin minus the temperature at A, that's 304.66 Kelvin. All right, and if I plug that in my calculator, my units would cancel out, and I would get that my change in internal energy is equal to 75.95 joules. Okay? That is from A to B. And because of my sign, right, it was positive, therefore the internal energy increased from state A to state B. All right. I should make sure that's the right answer. I actually didn't look at the solution sheet when I solved this. So we were looking for AB, 76. We got 75.95. That's close enough. I'm happy with that. Okay, so yeah, internal energy increased from A to B. Okay, what about the change in internal energy from B to C? Well, let's look at what happened from B to C. Oh, right here, temperature of the gas does not change during segment BC. So this is an isothermal process, right? And when it's isothermal, whenever we have an isothermal process, guys, so it's isothermal. And for all isothermal processes, change in internal energy is equal to 0. Okay? So that's our answer. That was quick. So since there's no temperature change, so there's no change in internal energy from state B to state C. Okay? Okay, and lastly, wow, this is such a long problem. Okay. Lastly, the change in internal energy from state C to state A is equal to, let's find out what happened from C to A. Okay, we have a constant pressure from C going to A, right? Actually, that goes from right to left, from C going to A. So we know that we have a compression in our volume as well, right? So I'm going to assume because we have a compression in volume, and that moves from right to left, I'm going to assume that that is going to be a negative value for work. But actually, we're not looking for work. We're actually looking for change in internal energy. So let's find out what that is. Anyways, so this is isobaric, constant pressure, right? From C to A. So we know that for all processes, isobaric, isothermal, or isochoric, we can use this formula. Right? Delta T. To find the change in internal energy. Again, we weren't given the value for CV, but we know that CV is also equal to, for a diatomic gas, 5/2R, right? And our change in temperature from C to A is whatever is TA minus TC, okay? And so I'll bring out the constant, 5/2, okay? And N is equal to 0.004 moles. R is 8.31 joules per mole Kelvin. Chose this value again because I want to be left with joules. And temperature at A we found to be 304.66 Kelvin. And temperature at C is minus temperature at C, which is 1218.62 Kelvin. All right. So I can cancel out the units and plug that in the calculator, and I would get that my internal energy, change in internal energy from state C to state A is equal to minus 75.95 joules. Okay. And because my sign for this is negative, I would say, so that means from A, the internal energy is less than the internal energy, because that's ETH from A minus ETH from C. Yeah, I would say that my internal energy at A is less than the internal energy at C. So therefore, internal energy decreased from state C to state A. Oops. All right. That was such a long problem, but thank you for bearing with me. And I don't think it was overly complicated, right? It was just a very long problem. So hopefully that helped. And if there were some questions on the information, please see the Chapter 19 summary video. Thank you.